Hi, welcome back. In this lecture I want to talk about one of the approaches of the dask collection, which is called dask.delayed. So dask.delayed provides lazy execution. And what does it mean? It means that instead of running immediately a task, it will build a task graph first. We will execute our task in a parallel setting only when explicitly triggering the method compute. So we will need to call the .compute method in order to actually execute. So that's what it means lazy execution. So why is that? Well, the reason for that, it enables efficient scheduling and parallel execution. So while we build the task graph, a task also can construct a task graph in an efficient way and optimize it. Dask.delayed also requires minimal code changes, basically just one decorator, and they support also dependencies and complex workflows. The example that I want to discuss in this brief lecture is the calculation of this integral of 0 to 1 of the f dx. This is a simple function. So how we do it with the Monte Carlo technique? Well, we basically take a large number of samples that between 0 and 1, and these samples will get in variable x. And then we take the square of the sample, and then we take the mean. This will be an approximation of our integral I that is defined here. So we can the first simple way is to call this function. We can do, for instance, serially in a sequential execution five times. So we give a different estimate at the different runs of the integral. So if you see here, we basically run this Monte Carlo integral and give the number of samples that is 10 to the 6, and we do 5 times. So we iterate 5 times. So this is a sequential. So we finish with the first simulation, and then we go with the second, the third, the fourth, and the fifth. Since we are using the multi-core, we can actually run the 5 simulation in parallel. So let's look at how to do that with the dask.delayed. It's quite easy. So what we need to do is to add a decorator before the function definition of our task. In this case is Monte Carlo integral. So we just add the decorator delayed before the function definition. So this will wrap around our function so it can run lazily. Remember now that these objects are delayed, so we explicitly need to tell dask to execute them. So now that we have created a delay function call, this is not executed yet. We have the task graph instead. In this case, if we print here, this Monte Carlo integral task won't be executed yet. So what we need to do in order to execute, well, we need to call the method compute. So when we call the method compute, all the computation will run in parallel across multiple CPU cores. So the task graph is created, and then we tell to execute it. Note here the star of the results. This is just a compact way to give our results, which is a list of delay objects. So the dask.compute star result just unpacks the list and schedule all the computation in parallel and execute it. So this star results is basically equivalent to this form here at the bottom. There's also a nice and useful method to visualize the task graph. We can do task.visualize star results, and in this case we are running 5 Monte Carlo simulation in parallel, and you see here the task graph. So this is 5 tasks. This is quite simple workflow, so nothing fancy, but you can recover the task graph by just calling dask visualize. There are also a number of additional functions such as persist and delayed. So delay is used for converting existing object into a delay computation. Persist is used for memorization. So it triggers the execution, but also keeps the results in memory for use. So it doesn't recompute. And so that's quite also useful if you have an easy and heavy function that on the same arguments you just want to save instead of recompute. This is the last slide of this lecture. Talk to you soon.